Hello, hello. I wanted to dedicate this screencast to percentage composition, which by definition is the mass percent as the mass of any substance divided by the total mass times 100. So depending on whether it's a compound or a mixture, it could mean something different. So let's take a look what it would be if you're thinking about a compound. So in terms of the PowerPoint, we would be somewhere around slide 15 is where I'm at. And I have a question there that if you take formaldehyde, which is CH2O, it's a toxic gas, and the question asks you what is the mass percent of each element in formaldehyde. Realize in case of formaldehyde, you have three different elements: carbon, hydrogen, and oxygen. If you consider carbon, you have only one atom of carbon, which basically means that you have 12 grams of carbon. So 12 grams are coming due to carbon, 2 grams are coming due to hydrogen, and I'm just using 1 for hydrogen, 12 for carbon, and 16 for oxygen for the sake of simplicity. You really could, in an exam, if this was an exam question, you would have to look at the periodic table that would be provided to you then. But coming back to what I was trying to tell you, I'm trying to determine the mass of each of the components, and my components in this particular case is the atoms of each kind. So all I have done so far is multiply the number of atoms by the mass of each atom so that I get the net weight contribution for each of those elements. And if you try to determine the total mass of formaldehyde, CH2O, you would say it's 12 because of carbon, it's 2 because of hydrogen, and it's 16 due to oxygen, totaling up to a 30. So 12 divided by the total, which is 30, times 100, is going to give you the mass percent due to carbon. Likewise, 2 divided by 30 times 100 is going to give you the mass percent due to hydrogen. And then 16 divided by 30 times 100 is going to give you the mass percent due to oxygen. When you work these numbers out, you should be getting a number close to about 40% for carbon, about 6.66%, 67 rather, because the 6 just repeats. And so there's two ways to figure out the mass of oxygen. Either you can just work the math out, so 160 divided by 3, that will be 53.33. Alternatively, you could say that since this is a percent, you can simply subtract 100 minus the summation of 40 and 6.67, and that should give you the same number as well. So the next question is then, why is it important to determine mass percent? What does it even mean? Realize that if I'm talking about formaldehyde, since the formula is CH2O, essentially once I have determined the mass percent of each of these element types for a given sample, I would always be able to calculate the amount of grams of carbon or hydrogen or oxygen, as the case may be, that I would be able to isolate from the sample of formaldehyde if need be. So for instance, if I ask you how many grams of carbon are there in 83.5 grams of CH2O or formaldehyde, you would say that since your mass percent was 40%, so 40% of the 83.5 grams, basically you're saying if you had 100 grams, 40 grams out of that is going to be carbon. So now if you have 83, how much would that be? So that's just a proportion that you're trying to calculate. 0.4 times 83.5, 0.4 times 83.5. I'm just trying to solve this this part. Plug in on your calculator, and 33.4 grams should be your final answer. So mass percent is a great method to figure out the percentage composition, because believe it or not, if you're thinking about a particular compound and it's a pure compound, then that percentage composition is going to remain the same. And you can kind of achieve the percentage composition. You can perhaps compare that to an unknown compound that you might have isolated in the lab, and the percentage composition is same, then in the pure state you can perhaps make a call that essentially your given compound is pure in a bulk sense. So that it's considered as a very important tool to determine the percent composition and hence be able to identify unknown material. So I want to focus a little bit on what is called as elemental analysis, which is this tool based off of the percentage composition. If you have, let's say, some grams of, and let me just erase this, we are talking about, I'm going to use black, elemental analysis. And let's say I have some x grams of some new compound that I isolated in the lab. If I'm able to determine the percentage composition, essentially by figuring out either A, the moles, or by determining the simplest formula, I would be able to determine the ratio, the minimum ratio that you can use for each of those elements. So there is the concept of empirical formula, which is empirical formula, which is the simplest formula. It's also the simplest formula. So what I mean by that is, if you have a molecule, let's say C6H6, this is an organic molecule. This is called as benzene, but one can perhaps envision that both carbon and hydrogen, the number of carbon atoms to the number of hydrogen atoms, they are 6 to 6 or 1 to 1. So both of these are divisible by 6. So you can say that the simplest ratio between them is 1:1, CH. So in terms of which one will be molecular formula and which one will be empirical formula, please realize that the first one that I wrote, that will be called as molecular formula, because that is the actual number of atoms that are present for that particular element in this compound benzene, whereas the empirical formula just gives you the ratio of the two. So that's one thing I want you to consider. Another thing that I want you to consider is that if you wanted to determine the molar mass of benzene, you would say, well, you have 6 atoms of carbon, so 6 times 12, plus you have 6 of hydrogen. That will make it 72 plus 6, total of 78 grams per mole. Now, if you consider the mass of this empirical formula, also called as the empirical formula mass, you would say that will be 12 plus 1, that's 13. So if you think about it, there is a relationship between the molecular mass or molar mass in grams per mole and the empirical formula mass that you're getting. And the relationship is that if you multiply the empirical formula mass by the number here, 6 in this case, you're going to end up with the molar mass. So one can say that the molecular formula mass, mm, let's say that is some integer n times the empirical formula mass. So if you knew one and you knew the integer, you would be able to determine the other, or vice versa. There is another thing that I want you to consider, and that is that the empirical formula you can have for two different compounds. Let's say you have a compound A, another compound B. Maybe A is acetylene, C2H2, B is benzene, C6H6, but both of those have the same empirical formula, CH, right? The value of N in one case is 2, in another it's 6. So that differentiates between the molecular formulas, but realize that empirical formula could be common for the two of them. And what I really want you to think about, and think about it real hard, is that empirical formula just is giving you the ratio of the two elements, and that's it. Nothing more than that. That means that at any given point of time, because the value of n's are different, you can have two different compounds which have the exact same ratio. In other words, the exact same empirical formula can be possible for two different compounds. Okay, I want to take the time to solve the problem that's given in, I believe it's slide number 17. Yeah. And it's based on empirical formula. The question here is, a compound of nitrogen and oxygen is analyzed. A sample weighing 1.587 grams is found to contain 0.483 grams nitrogen and 1.104 grams of oxygen. What is the empirical formula of the compound? So in this case, please realize that we have a total mass of 1.587 grams. Okay, and we are given that we have nitrogen, we have oxygen. Nitrogen, we have only 0.483 grams, so this has been found for you. Oxygen, we have 1.104 grams, and you're expected to determine the empirical formula, in other words, the simplest ratio between nitrogen and oxygen. Realize the total mass was 1.587, and so obviously the mass of nitrogen plus the mass of oxygen together, when you add the two, you should get the given mass. Now, in problems like these, when you have to calculate the simplest ratio, there are just a couple steps that you have to follow, and if you follow them right, you would absolutely never ever go wrong. So I do want to take the time to go over that in a methodical manner so everybody is on board with that idea. So let's just tabulate. Scientists kind of like tables, so I want to make sure everybody is on board with the idea. Nitrogen has an atomic mass. Nitrogen has an atomic mass of 14 grams per mole. Oxygen is at 16 grams per mole. Again, for the sake of time, I'm taking 14 and 16. If you're given in a test, if you're given a periodic table, please use the full 14.002 and 15.9998 for the case of oxygen. But like I discussed early on, that moles, the number of moles, is equal to given mass divided by molar mass. The given mass here is 0.483 for the case of nitrogen, 0.483. If I divide it by 14, I should get the number of moles. So I want to calculate the moles of nitrogen as well as the moles of oxygen. I'm going to do that for both of these. So we are calculating. Your step one is calculate moles of each element. And when you run the math, you should get 0.0345. Realize we started with 3 significant figures, so we are going to stick to that. For the second case, the case of oxygen, you're going to get 1.104 divided by 16. So 1.104 divided by 16 should be 0.069. So these are the ratios that we have obtained for the case of nitrogen and oxygen. So this formula kind of looks like nitrogen at 0.0345. Oxygen is at 0.069, which kind of looks like a very funky way of writing a formula. What must you do? The last step to do this, which is the second step really, is to get the simplest ratio. Simplest ratio. And in order to get the simplest ratio, one really must divide both the numbers by the smallest possible number. In this case, that smallest number happens to be 0.035. So you're going to first divide 0.0345 by itself. That will give you 1. And for the second case, 345, you're going to get a value probably very close to 2. As you do that, your formula becomes NO2. That is your empirical formula. So basically, there are only 2 steps. The first one is again to calculate the moles of each element. Once you've done that, simply pick the least of all and divide all the numbers by that least number, and that will give you the simplest ratio and hence also the ratio in case of the empirical formula. Okay, let's take it one step further and work on a problem where sometimes if we have been able to calculate the empirical formula mass, how we can utilize that to actually get the complete molecular formula. Let's work on that. There is a question on slide 19, I believe, on acetic acid. The question is, acetic acid contains 39.9% carbon. It contains 6.7% hydrogen. It contains 53.4% oxygen. The question is to determine, so this is what is given. The question is to figure out the empirical formula. What is that? And in addition, it has been given that the molecular mass is 60.0. And they're asking you to determine the molecular formula as well. There is a boatload of various different methods to do that, but the easiest one that I find most students can figure out is on the basis of what we have already seen. Since these are mass percentages, you need to take a step back and realize what that actually means. That means that if you have 100-gram sample, that would mean that you have a mass of 39.9 grams for the case of carbon. You will have 6.7 grams for the case of hydrogen, and you will have 53.4 grams for the case of oxygen. Now, if you were to determine the number of moles, we are going to take exactly the same steps that we have taken before. In order to calculate the number of moles for the case of carbon, you would say it's 39.9 divided by 12. For the case of hydrogen, you would say it's 6.7 divided by 1. For the case of oxygen, you would say it's 53.4 divided by 16. And you would solve that. This should be 6.7, of course. And I'm getting a number of 3.325 for the case of carbon. And when I plug in 53.4, divide that by 16, I'm getting a 3.3375. So here your lowest number is right here, 3.325. So I'm going to be working on getting the simplest ratio. Divide all these three numbers by 3.325. So this will come out to be 1. This is going to be 6.7. 6.7 divided by 3.325 sounds like it's going to be approximately equal to 2. Let's, for the sake of argument, let's find out the exact number, because I do want to tell you a rule. 3.325. 2.01 is what I'm getting, 2.01, so that can be approximated to 2. We are good with that. 3.3375 divided by 3.325, that should be approximately equal to 1. So sounds like my formula will look like CH2O. Now, if you think about the empirical formula mass, let's just call it EFM. That will be the mass of carbon, that is 12, plus 2 times hydrogen, plus 16 times 1. Total comes out to be 30 AMU. Turns out the molar mass is already given to you as 60. And I told you earlier that essentially molecular formula is just some integer times the empirical formula. So empirical formula times some integer is the molecular formula. And you should also remember that molecular mass is the same integer n times the empirical formula mass. Recall what we learned for the case of benzene. The 13 times 6, that integer was 6, was derived from the masses that were provided. So since I don't know what that integer is, even though I have figured out what my empirical formula is, I really cannot do anything about the molecular formula till I figure out that integer. But guess what? Since I'm given the molecular mass, so 60 divided by 30, because empirical formula mass is 30, that's going to give you n, the integer in this case, to be equal to 2. Let's plug that in. CH2O 2 times, and your formula becomes C2H4O2. I'm going to write down the molecular formula for acetic acid just for the reference point. So I got C2H4O2 as the molecular formula, and acetic acid in reality is CH3COOH. To consolidate, there are 2 carbons, there are 4 hydrogens, 3 and 1, there are 2 oxygens. So sounds like the formula that I got is the correct formula. Okay, the last problem that I want to solve here in this screencast before I move over to the stoichiometry screencast is another one where I have here a compound was analyzed to be 82.67% carbon, and it was analyzed to be 17.33% hydrogen by mass. And this again is something from your PowerPoint. This is slide number 20. Slide number 20. Okay, so what it says is that there is a compound, and when it was analyzed for mass percent, it was found to be 82.67% for carbon, 17.33% for hydrogen, and there was a molar mass that was determined, and that molar mass was found to be 58.11 grams per mole. And the question asks you, what you have to provide is the empirical formula again, as well as the molecular formula. So hopefully you can recall, we've already done 2-3 problems on this. The first step to do so is to determine the number of moles of each of the elements, and the second step is to determine the simplest ratio, and that will give you the empirical formula. So in order to determine the number of moles, one could say 82.67 grams divided by 12. That is going to give me 12 grams per mole, of course, for carbon. And for hydrogen is going to be 17.33 divided by 1. So this one will come out to be 17.33 And the other one, I'm going to just punch in on my calculator here. 82.67 divided by 12. And that comes out to be 6.889. Realize I'm not rounding up or down anything, because whatever rounding up or down has to be done, that has to be done way at the end. You really cannot do that while you're making your calculations, okay? So for now, you'll just say that you're going to go with 4 sig figs for the first number. And so what we have written is all right. The second step is to determine the ratio. All right, so we have here 6.889, which is the smaller of the two numbers. So you're going to divide both of the numbers by 6.889 to get 1 for the case of carbon, and for the case of hydrogen, you will get a number looks like greater than 2 but less than 3. On my calculator, that's coming out to be 2.515. So your empirical formula is looking something like C1H2.515. But guess what? Like we decided, the moles can never be fractions. So in a situation like this, you never want to round it up. You don't want to make the CH2.515. You don't want to round it up to 3 and call it CH3. Alternatively, you cannot round it down because this is more than 0.5. In fact, whenever your ratio is more than 0.3, let's say, and less than 0.8, so if it's in that range, you have to look for a lowest integer, which when multiplied by these fractions is going to give you the closest whole number. What I mean by that is, of course, you can't have 1, but what if you multiply this by 2? Then it's going to start looking like C2H5, right? Because 2.51 will be 5.03. So we can round that down to 5, and so your empirical formula in this case will come out to be C2H5. Now, again, in order to determine the molecular formula, you have to deal with the masses first. So you're going to determine the value of N, and in order to determine N, you first want to calculate the mass of C2H5. That's 2 times 12 for carbon plus 5 times 1, so that comes out to be 29 grams per mole. 29 grams per mole. And now when you try to determine the molecular mass, molecular formula, the molecular mass is given as 58. 58 divided by 29 will give you about 2, because 29 times 2 is 58. And that means that in order to get the molecular formula, you need to multiply the empirical formula that you have obtained, which is C2H5. You have to multiply that by this integer 2, as we have done previously. So the formula overall becomes C4H10, which is the formula for butane, the hydrocarbon that is present in your lighters, and that's called butane, and that is the molecule we have been talking about in this particular question. I think I'm going to stop here for this particular screencast. It already is about half an hour long. And in the next screencast, I'm going to discuss the concepts from stoichiometry. All right. Bye.